In this video, I'll give a high-level overview and explanation of our code, what it does, and how it works. So this time we're doing pattern matching on strings using the Rabin-Karp algorithm, but the implementation uses a few different data structures and algorithms, including a hash table, a hash set, and the Rabin-Karp string matching algorithm itself. So I'll go through each one in turn, and I'm going to start off with the hash table because that's one of the most important files we have, apart from Rabin-Karp itself. So, as we say here at the top in our comment, a hash table is a data structure that implements an associative array ADT. And what we mean by associative array is just a structure that can map keys to values. So we see that a hash table implements map, and the map extends an iterable, which receives entries, so a map of key value pairs. A couple of different things going on here. I suppose the main one to look at is the hash function itself. So the hash method calculates the hash value of a given key, see it's here, and it uses this to determine the index where the key value pair should be stored in the array. The method handles different types of keys. So you can see here, if the key we receive is a byte, short, integer, or a float, then our hash is just going to be an integer. If it's a number, then we're going to sum the upper and lower 32 bits of a long value. And then maybe the most interesting one, if it's a string, then we're going to calculate the hash for a string by summing all the ASCII values of the characters multiplied by 256 to the power of the position of the character in the string. And 256, we use this number, it's not just random, it's because that's the number of entries that we have in the ASCII table for extended ASCII. Finally, once it has the hash, then it's going to return the hash modulo the capacity of the hash table itself. The rehash function is also very important. Rehash is going to be called when the load factor is greater than or equal to 0.75. We talked about this thing called the load factor in the report. So the load factor denotes how full the hash table is allowed to get, or its capacity is going to be automatically increased. And the load factor is given by total number of items divided by the size of the array. Back down to the rehash here. We're saying when rehash is called, we're going to create a new array of entries with double the original capacity. We'll iterate through the original array. We'll calculate the hash of each of the keys. And then, I say we haven't seen the put method yet, but it's the same procedure we go through. We're just copying all the entries from the original array into the new array. So here we find the index where the entry is going to be placed, iterate through all the non-null entries and find the key or an empty slot, and just stick it into the new array down here and set the value of our original array to the new array. Other methods, of course, we have get for retrieving one of our key value pairs from the hash table. We have put. I mentioned there that the kind of the functionality here that we use in the rehash is pretty similar to the put. So what that does, what it's going to ask first off, if we've exceeded the load factor. So if the load factor is greater than or equal to 0.75, then run rehash, which we just saw. Otherwise, we'll continue. And we'll just find the index in our existing array where the entry that we're trying to add should be placed. Iterate through all the non-null entries in the array until we find the key or an empty slot. And then we said that if we're updating, if the key that we're going to update is already in the table, then we're going to update its existing value. Otherwise, we're going to find the next empty slot in the array and place that entry there. Of course, inversely, we have remove. It's just going to iterate through until we find the key, take it out, and return null if we didn't find anything. Or it's going to return the val if we found the value. These ones down the bottom, I guess they're kind of similar. We have keys, values, and iterator. They're all iterators, but the difference being that keys only returns the keys. Value only returns the values, whereas the iterator returns key value pairs. Maybe the next thing to look at is going to be the hash set, I think. So the hash set is similar to the hash table, but it doesn't implement an associative array like the hash table does. It only stores single values. So we saw how the hash table implements a map, key value pairs. The hash set only implements a set where it just takes one value. So the set means that the values are going to be unique. Everything in the set is only going to have one of each, no duplicates. suppose it's got some similar methods. It still has an iterator. As expected, we have a method to check if it contains a certain value, adding values, removing values. We have these ones: add all, retain all, and remove all. There's some comments describing this. So add all is going to add all the elements from the set that we've passed in the arguments to our set. Retain all is going to look at what we passed in the arguments there, and it's only going to keep the elements in the set that are also in the existing set. So where there's an intersection, I suppose. And remove all is going to do the opposite. It's going to remove all the elements in set S that we passed from the current set. So it'll look at the intersection and say, okay, if this element is already in the existing set, then remove it. That's it for the hash set. I'm going to move on now to RabinKarp itself. So this is definitely the bones of what we've done. The RabinKarp algorithm it's a string searching algorithm, or a string pattern matching algorithm that uses hashing, like we just saw in our hash table, to find any one of a set of patterns in a text string. And the algorithm works by calculating a hash value for the pattern that we're looking for, and for each substring of the text of the same length as the pattern. I guess this sounds kind of abstract when I talk about it here, but if we look at main, you can see an example of how we might use this. We say, okay, here's this pattern. It's ridiculously long. We have this text string, and we're saying to RabinKarp, okay, we want to find if and where this text is pattern, or sorry, if and where this pattern is present within the text. So RabinKarp is going to use hashing to do that. You know, the alternative would be to go through each of these characters, say take out 3 characters at a time, slide a window across and say, okay, did I find it yet? Did I find it yet? That's ridiculously inefficient. So instead we calculate a hash value for these characters, and we just compare the hash values instead. So it's going to create a hash value for this text that we're trying to find and for the pattern that we're looking through, and it's going to check if the hash values match. It'll say, okay, if the hash for the pattern and the substring are indeed the same, then we've got a match. But that's so much more efficient than taking all the substrings directly, especially for much longer patterns and larger texts. So the first thing to look at in here is this hash function, which uses the formula it's given up here. So it takes hash, this value d, this value q, we'll look at them now, takes d multiplied by a hash value plus a character value modulo q, where d is the number of characters in the input alphabet. D is going to be the length of the pattern. Q is going to be the prime number used as the modulus. And we're going to run through that formula for all the characters in the string that we've passed, and that's how we return our hash value. We mentioned this d and q. We have the value of d set to 256, which again isn't a coincidence. 256 is the number of characters in extended ASCII. This value 101, again, might seem kind of random, but this is actually a prime number. And we could use any number we want, but we use prime numbers because the result is going to be a more even distribution of hash values, which makes it less likely to cause collisions where we end up with the same hash value for multiple patterns. You know, prime numbers, we're not going to get the same thing twice very often. Next thing to look at is the RabinKarpSet itself, which is the main function in here. And that's going to actually find all occurrences of a pattern in a text string using the RabinKarp algorithm. It's the actual implementation of RabinKarp. So first thing we do in here, we receive a string we want to find. We receive an int m for a length, and we receive a set of patterns. Well, it's not a set yet, but we're going to turn it into a hash set. We say, okay, we only want to consider each unique pattern once. We're not going to have duplicates because that would just be pointless. We're going to create a hash set from the patterns that we received to get rid of all the duplicates. Then we're going to create an empty hash set to store our hashed patterns. Once we've received our set of patterns, we're going to iterate through our patterns and create a hash for each one, adding it to that empty list of hash patterns that we have up here. We're going to compute the hash for the first substring of length m, which in our case m is just the length of the pattern. We passed in here pattern length and the pattern itself, so m is going to be pattern length. So we're iterating through the string and checking if the hash of the substring matches the hash of the patterns. If we found a match, then yep, we've found our pattern, or we found a match for the string we're looking for inside our pattern. Otherwise, we've reached the end, we just break, we didn't find a match. But this most important part down here is the rolling hash function. And the idea here is that it's going to allow the algorithm to calculate the hash value of the next substring in our little sliding window from the hash value of the current substring in constant time. So we're taking, say for example, if we were taking 3 characters at a time, we're going to move forward and forget about that first character and add another character to it for our next set of 3. This rolling hash function allows us to do that in constant time. And it's done by subtracting the contribution of the first character of the current substring that we're looking at and adding the contribution of the next character after the current substring. We would say characters, say we have 1, 2, 3, 4, 5, 6, and we first looked at characters 1, 2, 3. We say, okay, next I want to look at the next 3. We forget about the first character and we add on the next character. And that way we slide our window across in constant time. And this rolling hash function, it's going to greatly improve the efficiency of the RabinKarp algorithm. And this is what makes it suitable for running on very large texts. I suppose the next thing to look at is just the main function, where we actually instantiate a RabinKarp object and run this RabinKarpSet function on it. So I'll run this and just show you what happens. Experiment, switch back to main. And there we go, it's telling us that it found our pattern inside our text string at character 400. And yes, got 400 characters. So the algorithm works to tell us that it found the pattern that we were looking for inside our text string at character number 400. Thank you for watching.